Hello, everyone. Welcome. We are super excited to have Dr. Clarissa today here with us. She is a postdoctoral fellow at Caltech, and she studies astrophysics. She's going to be giving a really awesome, exciting talk on imaging other planetary systems. So we're going to be learning about exoplanet systems and how we take these pictures. So without further ado, let's tune in for our really exciting talk.
Thank you. Hi, every. Hi. No, maybe I'm. Hello. Oh, yay. Okay. Hi, everyone. I'm Clarissa. I am a postdoctoral fellow at Caltech studying astrophysics. Um, so specifically, I am studying direct imaging of exoplanets, which we are going to learn about today and talk a little bit about. And I'm working on very exciting NASA missions that are coming up, like the Roman Space Telescope and the Habitable Worlds Observatory. So I figured it would be a good idea to start by understanding our place in the universe and kind of where we belong. And let's just start by zooming out a little bit. So we're all here at UCLA at Exploring Your Universe. If we zoom out a little bit, we are in the LA area here in California. If we zoom out even more, we're in the US. Let's zoom out a little more. We're here on planet Earth. And if we zoom out even more, we are just one out of the 8 planets in our solar system. So we have 4 rocky planets, Mercury, Venus, Earth, and Mars, Earth being our home. And then we have 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. And unfortunately, Pluto is no longer part of the family. So we are all orbiting our star, the sun. And if we zoom out a little bit more, the sun is only one star out of the more than 100 billion stars in our galaxy. Do we know what the name of our galaxy is? Nice. Yes. So we are here in the Milky Way, just one out of the 100 billion stars. So one thing that we can ask ourselves is if these other stars, including the ones that we see in our night sky, could have their own planets, just like the sun has the planets in our solar system. And who here is into Star Wars? Just raise your hand. Good. Me too. Yeah, so in Star Wars, we see other planetary systems being referenced all the time, right? So the story is set in a galaxy far, far away, and we see all of these planetary systems that Luke and Skywalker and other characters travel through that are not all in the same star system. So for example, Coruscant is not in the same star system as Naboo or Tatooine. And I even pulled out, I didn't know that this was a thing, but apparently there is a map of the Star Wars galaxy with the different star systems and the different planets that can host life in these star systems, which is really exciting. Similarly, who here is into Marvel, like the MCU? Do we like that? Do we still like that? I actually haven't kept up with it, but I like the older movies, like the Avengers and stuff. Yeah, so in Marvel, we also see a similar thing, right? So we have the Earth, which is where the Avengers are from. But then we also see these other worlds that are in other solar systems different from our own. One example of that is Vormir, which I thought was... Hello? Okay, sorry, the microphone. I thought was really intriguing. So this is the Vormir planetary system, which is, if you remember Avengers Infinity War, that's where the Soul Stone is. So it's in a different star system from our solar system. So one thing that we can ask ourselves then is if there are these exoplanets, these planets around other stars, these other planetary systems, how can we find them? And one thing that we want to make clear from the beginning is that everything that we have learned about space and about our universe comes from technological advancements and understanding how to manipulate light. So for the longest time, our best tool for learning things about space was actually just our eyes, which is about 300,000 years old. And we can see quite a few things in space with our eyes, like we can see some of the stars, not all of them. We can see some planets in our solar system, also not all of them. But if we want to see even further, we need to learn how to manipulate light so we can see better than we could before. And the oldest telescope sort of instrument is about 400 years old. And it allowed us to see things that our eyes just could not see. So one example of that is Galileo and Jupiter's moons. So Galileo pointed his telescope up, and he actually saw Jupiter's moons, which are these 4 dots around Jupiter that we just cannot see with our eyes. And he noticed, very interestingly, that the positions of these points were changing every night because they're moons orbiting around Jupiter. So we've come a long way since Galileo, and with the more powerful telescopes that we can build, the more discoveries we can make. And these are actual telescopes that we use to collect data to learn more about our universe, including about finding exoplanets. So here we have some examples of actual telescopes that have detected exoplanets. Some are on Earth, here we have in space. So there's just quite a few of these. One big challenge when it comes to finding these exoplanets, though, is that planets are really small compared to their stars. So here I have the solar system to scale. We have the Earth and the Moon right here. Jupiter is our largest planet, and it can fit all the other planets in it, and still you would have some space left. But the Sun, our star, doesn't even fit in this light because it is just so much bigger. So it makes this makes finding exoplanets a lot more challenging than we would like. So there are a few indirect ways that we can find these exoplanets by actually looking at the star, which is a little bit easier because those are bigger and brighter. So one thing that we can do is we can actually track the star's brightness over time. This is called the transit method. And if we see a dip in the star's brightness as the passes in front of it or transits the star, then if we see this happening over and over again, then this means that there's likely a planet orbiting around that star, and we just see this transit dip over and over again. Similarly, we can track the star's changing color or different wavelength shifts as the planet and the star both orbit around the center of gravity of the system. If we see the system from an edge-on perspective, the star is going to be moving back and forth from our perspective, and we can actually see small changes in its color, small shifts that are periodic due to a planet orbiting around it. However, these methods don't actually take a picture of the planet. We just infer that the planet is there by looking at the star. So how can we actually take pictures of these planets and see them? So here, another challenge that comes in with the planets being much smaller than their stars is that they are also much fainter than their stars and really close to the stars. So it's very difficult to image planets because they get lost in the star's glare. So in order for us to actually see the planet, we need something that can cover the light from the star so we can reveal the very faint light that's coming in from the planet. Generally, on telescopes, what we do is we have an actual physical blocking of the star. It's called a coronagraph, and it allows us to actually image the very faint light coming in from the planet. Now, this is not a trick question, but if you were an alien and you wanted to image our solar system planets, do you think you would find the Earth or Jupiter most easily? Just shout it. Yes, like I said, not a trick question. Jupiter would be a lot easier to image. And the reason why is because not only is Jupiter bigger, more massive than the Earth, but it's also a little bit further away from the sun, which helps with actually separating the light from Jupiter and the sun, and therefore making sure that we can actually image the very faint light that's coming in from Jupiter. However, because of this, even the most powerful telescopes that we have cannot image another Earth just yet. So 2 examples of those, one on the ground and one in space, that I've actually worked with before, are the Keck Observatory, which is the largest telescope on Earth, and the James Webb Space Telescope, JWST, which are 2 of the most powerful telescopes we have. Currently just do not let us image planets like the Earth. So here I have some actual images of other planets, so exoplanets around other stars. And let's break down what's happening here. So like I said, we can't image things like the Earth. We can image very massive planets like Jupiter, but do have to be really far away from their stars. And they're also, in general, really young, a few millions of years old. Our solar system is 4.5 billion years old, so significantly older. So here, let's break down what's happening in these images. So in each image, we have the star in the center being covered by the coronagraph. We don't like the light from the star. We want to cover it so we can reveal the faintest planets that we possibly can. And here, the little bright dots are the actual planets. This is the light that's coming in from the planet. And one thing you might notice on the leftmost picture is that the size of Jupiter's orbit, which is about 5 times further away than the Earth is from the sun, is actually within where we cover from our coronagraph. So we couldn't even image Jupiter if we wanted to, because it would be just too close to its star. So currently we can only image planets that are gas giants that are really far away from their stars. One very special system that I always like to talk about, because it is my favorite system, is just so interesting, is the HR 8799 system. So this system, again, we have the star here in the center being covered by the coronagraph, and then we have these 4 dots. So these are 4 gas giants that are orbiting around this star. So just to put it in perspective, the closest gas giant, this one, is about 3 times further away from its star than Jupiter is from the sun. And this one is about 6 to 7 times further away. And they're all 5 times more massive than Jupiter. Jupiter is the largest planet in our solar system, and this system has 4 of them. And they're all really far away from its star. So I think it's just really interesting to think about this system. If we think about it from a population perspective of the current exoplanets that we have found, so just recently we hit 6,000 exoplanets that were discovered around other stars. And here they're plotted with the different colors being the different discovery methods. And the semi-major axis is in the x-axis. You can think of it as the distance between the star and the planet, and the mass on the y-axis. You'll notice that the orange planets, which are the planets that we have imaged, are on the upper right-hand side of this plot. And that's exactly because of how hard it is to actually image things that are closer to their stars and also less massive and therefore a little fainter. So all of the planets we have found with direct imaging are 10 times further away, at least, from their stars than Earth is to the sun. And they are about 10 million times fainter than their stars. So therefore, they're all gas giants that are at least 1 mass of Jupiter. To put this into perspective, keep this in mind, 10 million times fainter than their stars. If we wanted to image something like the solar system, we would have to image something like Jupiter. We would need to have a telescope that's capable of imaging something that is 1 billion times fainter than the sun. If we want to image something like the Earth, we would need to image something have a telescope that's capable of imaging something that's 10 billion times fainter than the sun. And you can see how challenging this is by how easily we just lose all of the rocky planets in this image here. Yeah, so our main limitation is actually our ability to image these fainter planets that are really close to their stars. But that's the final goal for direct imaging as of now. We would really like to be able to image something like the Earth around a sun-like star. Because as far as we know, something like the Earth, a planet like the Earth, is the only kind of planet that can really host life as we know it. So the main solution is to actually improve our technologies so we can better control light that's coming in from the star, so we can cover it more efficiently, and we can actually reveal the planets, the very faint lights that's coming in from the planet. So a few things that we do on ground-based telescopes is we use adaptive optics, which is super important to correct the light that's coming in, especially as it goes through the atmosphere. To image something like the Earth, even if you were in space and you didn't have to worry about the atmosphere, it's actually really challenging to control the light enough to be able to see something like the Earth. And we want to get better and better at actually covering the light from the star so we can get closer and closer to it as well. And our final goal, which would be very exciting, would be to image another Earth around a sun-like star. So here I just have an example of a simulated image of what this would look like. So if you were an alien looking at our solar system and you covered the light from the sun with your coronagraph and your very powerful telescope, you would be able to image the rocky planets Venus and Earth, and then Jupiter up here. And like I said, we are not quite there yet, but upcoming telescopes, especially the ones that are coming up, there's one next year that I'll talk about, and another one in the 2030s, 2040s, will allow us to do this. So specifically, and I'm really excited about this because this is actually what I'm working on, NASA is going to be taking a very big lead on this. So the next NASA Space Telescope, the Roman Space Telescope, which will launch next year, is actually going to be capable of imaging planets that are 1 billion times fainter than their stars, which means that we would actually be able for the first time to image something that is more of an analog to Jupiter in our solar system. And if the technologies that we have up in this telescope prove to work well enough for this, then we would be capable of launching the Habitable Worlds Observatory, which the final goal would be to image something like the Earth around another star. So 10 billion times fainter than its star, which is very challenging. I wanted to quickly talk about this before I finish up, and then I will take more questions. But I just wanted to say that NASA has taken a really big lead on this. We have accomplished so much thanks to NASA. However, the budget for NASA is potentially facing a 47% cut next year, which could delay or even cancel these missions, including missions that would really allow us to put our place in the universe more in perspective. So if you have any interest in taking action on this, you can scan this QR code and it will take you to the Planetary Society's website where they can tell you a little bit more on how to take action. But I wanted to leave some time for questions, so I'm just going to finish up. Yes, I'm going to finish up. Thank you so much. And if you have questions, please just let me know. Okay. Yes. Equipment at home for viewing exoplanets. Ooh. I actually don't think that any backyard telescopes are capable of looking at exoplanets. You could not image an exoplanet with equipment that we have at home. The main challenge is that you need bigger telescopes because you need better resolution to actually be able to separate the light from the star from the light of the planet. So I don't think any telescopes on like that we buy for our backyards are large enough to allow us to do that. And it requires, like adaptive optics, which is a whole set of systems that we actually also don't sell like off the shelf, as far as I know. A good question. Yeah. The most memorable experience, what? Sorry? Oh, I think it was definitely going up to Keck Observatory. I got to actually take data on some of these planets that we have already found. I'm really interested in understanding their orbits and how they formed. So we wanted to take additional data to basically have more information on their orbits. So I think definitely going up to Keck and seeing, oh my goodness, this is real. Like we have an actual, large telescope like this that's actually taking data. I feel like when you do things, especially remotely, right, you don't realize, how large some of these things really are. So yeah, definitely that. Yeah. Yeah. If I remember them. Huh? Okay. So let's see. I think so. The top left one, I think, is Lick Observatory, which is up in the Bay Area. The bottom one here is Hubble Space Telescope. This bottom middle one is Palomar Observatory, which is not too far from here. You could actually drive up to it. I think. Oh, so that up there it's ALMA. I'm trying to remember what this one is. I think it's Gemini Observatory. So there's two of them. There's one up in Hawaii, which is Gemini North, and then there's one down in Chile, which is Gemini South. And they're exactly the same, which is why they're called Gemini. And then the bottom right one, I think, is that No, it's not Subaru. Oh, that's the VLT, the Very Large Telescope. Yeah. Which is also in Chile. So most of the telescopes we have on the ground, they're either in Hawaii or in Chile, like the really large ones. We basically want to be in a place that is high altitude, fairly dry, so deserts are good for that. That's why in Chile, you'll see a lot of telescopes. And in Mauna Kea in Hawaii, there's also quite a few. Yeah, so all of these, or some of these are up there. But then we have two here in California, Lick and Palomar. But they're not as big as the ones in Hawaii and Chile. Yeah.
Thank you. Compared to simulations we'll talk about in your talk, do you think the exploration in an actual planet, that actual planet will not be seen in spot because there will be artificial light and also human activities there?
I don't think that would affect things too much, to be completely honest. And the reason why is, so one thing I didn't mention is that right now we can only image planets in the infrared. So that's why we can only image planets that are younger. They're hotter when they form, so it's a little easier to see them. So that's, and that's completely dependent on mass, which is why we can mostly detect planets that are more massive, like Jupiter planets. For the Habitable Worlds Observatory and the Roman Space Telescope, we're going to be imaging planets in reflected light for the first time. And potentially a civilization, if there was one, would, have more visible light that would create more of a reflectiveness, but that's actually not what matters the most. What matters the most is the composition of the atmosphere. You want things there that are, could be more reflective. One example of that is like water vapor. So we could see that. We could see the components of the atmosphere if we image the planet. Yeah. Yeah. Oh, yeah. Yes. Yeah. I didn't talk too much about this, but the atmosphere is a huge problem. We could not even have hope as of now to image something like the Earth with a ground-based telescope. It would just be extremely challenging. Some telescopes might be capable of imaging less massive planets if they're larger. So for example, the extremely large telescope ELT, which is coming up, it's European-led, but it's coming up in like about 3-4 years, would be capable of doing that. But if we want to keep things like the telescope itself, if it doesn't have to be that large, then we definitely want to be in space. We want to avoid the atmosphere because it is a huge issue for actually allowing us to image these planets. Yeah. I have a backup on this one. Yes. Okay. So, so the resolution, we want to see things that are going to be, so of course this depends on the distance from here to the system. But if you were to look at the solar system 1 parsec away, you would have the Earth at about 0.1 arc seconds. Jupiter would be at about 1 arc second. And all of the planets that we can currently image are generally, further away from that, unless they're really bright, in which case resolution itself is not the main limitation. The problem is not just the resolution; it's also how faint the planet is. Does that make sense? Yep. Yeah. Yeah. So. For imaging planets specifically, some of the most powerful telescopes we have are the Keck Observatory, which is the largest telescope on Earth. I showed a picture of it. And actually, UCLA also has a lot of work that uses the Keck telescope? Yeah. So the one up here on the left, so that's the most powerful telescope we have on Earth. In space, it's definitely James Webb Space Telescope, JWST, which is here on the right. So that one is the most powerful telescope we have in space right now. And the Roman Space Telescope, at least for imaging planets, is going to be even more powerful than JWST. Oh, I don't know. Actually, it's a good question. When I went with a support astronomer. So I don't know if you need to have someone, like, I know there's a bunch of requirements, like you have to rent a Jeep to go up to the summit. Like very specifically, it has to be a Jeep that is rented. And then I think you might be able to schedule tours to like go up to there's like a point in between, like where the telescope actually is, which is all the way up in the mountain, and like, you know, like sea level. And you can visit that, which is like the visitor center. But I don't know. That's a good question. Yeah. Yeah. Detect what? Sorry? If they would be able to detect us, their telescopes are good enough. I guess they would. Yeah. Yeah. Oh, okay. Oh, I started later.
Oh yeah.
I started like 5 minutes later.
Oh.
Yeah, yeah. Any more questions? Yeah.
Mentions during the atmosphere of exoplanets. How do you tell what's in the atmosphere?
Yeah, so for that, you not only need to have a telescope that's powerful enough to imaging the planet, you also need a spectrograph that's powerful enough to actually look at the different wavelength compositions of the planet. And we have a pretty good idea of, and this has been done with the planets that we have already imaged, we have a pretty good idea of what certain molecules would lead in terms of like absorption lines for specific wavelengths. So we can find out what's in the atmosphere. Depending on the wavelength range of your telescope, that might change what kinds of molecules you could image or you could detect, but that has been done before. And yeah, that's one really exciting thing about direct imaging, actually, is that it allows you to look at the light from the planet itself, which means that you can actually look at what the atmosphere of that planet is made of. Yeah. Yes. Yeah. So a few things that we have to worry about, beyond being at the capable of imaging the planet, is if it's in the right distance from its star, which means it has the right temperature, but also in the atmosphere itself, things that we care about are like, having water, CO2, things that are, similar to our compositions here on Earth.